All right. Well, here we go. All right, we're going to finish stuff today involving solutions, and we're going to start the next topic just a little bit, just enough to whet your appetite so you want to know more, or scare you to death about it, whichever is applicable. And I've got forms for people to pick up. Not too many. That's not to pick up. That's mine. You can't have that. Let's see. So anything there's tests left over also from accessibility and testing center and stuff like that. So on solutions, we're used to thinking about them being aqueous, liquid-based solutions. There are other types of solutions that are worth mentioning, at least a little bit. Gas solutions, like air. Of course, air is a common example of a solution. Gases are infinitely soluble in other gases. It doesn't matter if the molecules are polar, non-polar, hydrogen bonding, any of that. It doesn't matter. Water vapor and argon, you can combine them in any amount you want. They're both gases. One is atomic, so it's non-polar. It only has dispersion forces. The other has hydrogen bonding between the molecules. But in the gas phase, the molecules are too far apart from each other the vast majority of the time for any intermolecular forces to make a difference. So there's no like dissolves like with gases. It doesn't matter if they're polar, non-polar, atomic, molecular, whatever. All gases are infinitely soluble in other gases because they're mostly empty space. And the molecules can fit in among each other and not even care what the other molecules are. So air and other mixtures of gases like that are solutions. Solid-solid solutions do exist. Waxes are interesting kind of solid-solid solution. This is going to be great. Do you want to blow more stuff up before the end of the semester? All right, okay, so it's not today, but some point. But when we do, I found some leftover candles at home. I think I was talking to somebody the other day, and I said these were cinnamon flavored, and flavored would mean you eat them. I meant scented, but it'll smell so good when we blow up some more hydrogen because these are cinnamon candles. Those are wonderful. So, but that's wax in a candle or something, and waxes are a solid solution of mostly organic material. Metals form solid solutions often that we are familiar with, called alloys, types of steel, brass, bronze, sterling silver. These are solid solutions called alloys. And usually it's one metal dissolved in another. It doesn't have to be a metal. But a substitutional alloy might be something like sterling silver, which is mostly silver, 92% silver or something, the rest copper for the properties of hardness and stuff for your alloy. But the copper and silver atoms are roughly the same size. If you find them on the periodic table, they're not identical. They're both in group 1b, 11 if you insist, on the periodic table. But in the pure silver, if you imagine pure silver, in the solid state, the silver atoms, we usually treat atoms as if they were roughly spherical. They're not perfectly spherical objects, but then again, they're not really objects so much as clouds of electron density, right? In the solid state, if you model the atoms as spheres, this is in Chapter 12 in a section that we don't do extensively because it's one of the things that you got to pick and choose which things you're going to do and not do. Imagine the produce department. If they have oranges, and they're all the same shape and size, and they're all nice spherical oranges, lay out a layer of oranges, then the second layer of oranges would stack in the crevices in the first layer, right? They're spheres. They don't pack with perfect use of space. There's some wasted space, so to speak, in between the spheres. But you couldn't replace the orange with an apple of similar size. You couldn't put an apple of similar size without replacing an orange, is what I mean to say, right? You'd have to take out an orange, replace it with an apple, because they're similar sizes. So sterling silver is an example of a substitutional alloy, where atoms of the solute replace atoms of the solvent in the solid structure, because they're similar in size. Another kind of alloy is something called an interstitial alloy. An example of this would be something like a carbon steel that is mostly iron with a little bit of carbon in it. Carbon's not a metal, but it is a solid, right? And it doesn't have to be a metal necessarily. We're just talking solids dissolved in solids. Carbon atoms are a lot smaller than iron atoms. The carbon atom would be kind of a grape if the iron atom were an orange. And you can fit the carbon atoms in the crevices in the crystal structure of the iron without replacing the ions, because there's a difference enough in size. Remember, if you're packing spheres, there's going to be some essentially wasted space between the spheres. When you stack the second layer on top of the first, there's going to be airspace in between those oranges. If you imagine that as atoms, same principle applies. The second layer can pack on top of the first, but still there's empty space. And if another kind of atom is small enough, it could occupy some of those empty spaces. Not all of them, but some of them. So the carbon would be your grape to your iron being your iron being your oranges in the stacked produce or something. So an interstitial alloy is the name for that. Interstitial, the interstices are the gaps, the spaces in the crystal structure. Interstitial is a less common word. I used to have these in the opposite order for whatever reason, but it seems easier to build to the more complex word. You hear that word interstitial in other contexts sometimes. It's always something where something is fit in between or among other things. I have a friend who, for a period, was working at a TV station selling advertising, among other things, and they would have interstitial segments. They called them. It was just a little segment they would stick in between other programs or even other commercials. So, same word, same meaning. So those are solutions that are not involving water or any other liquid. There are such things. Okay, so they don't have to involve liquids, but usually when we think of solution, we think of something with water, right? That's the most common. But there are other solutions. Now, solutions that we've been talking about, again, the solution is a homogeneous mixture. If I can just read from the screen in front of me, a homogeneous mixture is a solution by definition. Solutions don't separate, they're visually uniform. At the other end of the spectrum of mixtures, there are heterogeneous mixtures that settle out eventually. And such mixtures are visually not uniform. And we call those usually suspensions. A crude suspension might be if you're at the beach and you got a pail with water and you throw sand in it and swirl it. The sand swirls around and settles out pretty quick. It's not a suspension very long before it really becomes two separate things. If you're taking the qual lab, if you were doing the cation experiments and you had the 3-inch test tubes and you make your precipitate, you put it in the centrifuge, you're taking advantage there of speeding up the process of settling out a suspension. That solid is suspended in the liquid, in the water, and it would settle out eventually if you were willing to wait. But let's face it, it's chem lab. You want to get out of there as fast as possible, and so you put it in a centrifuge and speed it up a little bit. Suspensions are also things like any of those drugstore products that say shake well before using, like milk of magnesia. If you don't shake it up, the blue bottle of milk of magnesia, if you could have it in a colorless clear bottle, you would see it's all kinds of solid stuff sitting at the bottom and not very much in solution at the top. You have to shake it up so you get a uniform dosage. Otherwise, if you just pour it out, that first dose from the top would be mostly water and it wouldn't do much. And the bottom, if you drank the sludge, it would like blow out your colon or something. So it's better to shake it before using. Pepto-Bismol, other products like that, suspensions. Okay, so if it says shake before using, probably a suspension. Now, in between suspensions and solutions are interesting things called colloids. A colloid is a dispersion of one substance in another in such a way that the dispersed particles are small enough that they don't settle out, but they are large enough that they scatter visible light. They have a size usually on the order of 1 to 1,000 nanometers. And if you recall in Chapter 7, I want to say it is, the electromagnetic spectrum, visible light is from 400 to 750 nanometers in wavelength. So this covers visible light as well as sort of near infrared and ultraviolet wavelengths. You don't drive in a foggy situation with high beam headlights, right? They say don't use high beams in the fog because it does more harm than good. The light scatters in the fog because fog's a colloid. Colloids scatter light beams because the dispersed particles are on the order of the same size as the wavelength of visible light. So the droplets of water in the air, they don't settle out. They stay dispersed in the air. And we call that a colloid. Fog is one example of a colloid. Smoke is a colloid that involves a gas dispersed in a solid. And there are other colloids on this list here that's found in, again, that's in Chapter 13. near the end of chapter 13. I don't know where the table number went, but it's there. There's some delicious colloids, right? There's whipped cream, marshmallow, milk, butter, paint, not paint. I guess we're out of delicious ones after butter. Paint. So lots of things that you might not have thought were, not a solution. Turns out they are solutions. The big beaker with the dry ice that we had with the indicator. There was fog coming off of that, right? It was cold enough that there was water vapor condensing into droplets. If you shine a laser pointer through that fog, you don't see it in the air, but you do see it in the fog, and that's because air is a solution. It doesn't scatter light beams. Fog, a colloid, does scatter light beams. So you can tell something about the size of the dispersed particles by whether your laser pointer or your headlights or something are visible in it. Headlights don't have beams in clean air, but if there's fog or smoke or something, then you do see them. It's not worth memorizing the names of these. Like the ones that involve a gas dispersed are called aerosols. These ones, emulsions and sols and solid sols. Oh, emulsion. I remember you get enough chemistry geek people together. It was when I was in graduate school. That's when it was. There was a event every spring semester. They'd bring in prospective graduate students they wanted to try to recruit to come to Purdue, and they would they'd have a dinner Saturday night after all these day and a half of meeting with professors about research. And it was at a Japanese restaurant in downtown Lafayette, Indiana, and there was a karaoke thing. That it turns out it was $1 a song, but nobody knew this. I don't know who paid. But there was a whole bunch of chemistry people singing along to Aerosmith, changing the songs to Sweet Emulsion. It was really terrible. But that's a colloid. That's my favorite colloid memory, for what it's worth. Now, there are only 8 things on that list. If you figure there's 3 states of matter, so if each state of matter could form a colloid with the other 3 states, there should be 9. Why are there only 8? What's not on here? Gas in a gas, right? Because gas forms a solution with any other gas. Doesn't matter what the gases are. So a gas-gas colloid there is no such thing. But you can disperse a gas in a solid or liquid, a liquid in a gas, solid, or liquid, or a solid in a gas, solid, or liquid and get a colloid. Gas in a gas is a non-existent colloid. It's a solution. So don't memorize emulsion, foam, all those things for any sake for our class. But it's good to be aware that those are all kinds of colloids. It makes for an easy exam question, right? Pick the colloid. A, fog. B, salt water. C, copper. Something corny like that. It's supposed to be automatic points if you're here that I'm telling you it is. Okay, so you're welcome. Okay. So anyway, those are some other types of mixtures that are beyond the ordinary solutions we're used to thinking about, like aqueous compounds. So it's worth being aware of. As a sort of interstitial thing between 2 things about solutions, I stuck it here mainly because in case there was one of these semesters where we got 2 snow days and you lose a whole week and you're looking for stuff to cut, this would have been easy to cut. So I put in the position it was in. We might get a snow day in April for all we know, but this page just has a couple of interesting things about water that are worth pointing out. We do have the time. Compared to some other liquids, water has an abnormally high surface tension. Surface tension is exhibited when the molecules on the surface of your liquid have strong intermolecular forces around them and below them because there's nothing above them. Now, consider a molecule down in the bulk liquid, below the surface. A molecule below the surface, it's got hydrogen bonds. Let's say it's water. It's got hydrogen bonds above it and below it and to the left and the right or side to side. Usually there's about 4 hydrogen bonds per water molecule. But let's say it weren't water. Let's say it was some other molecule with dispersion forces or dipole-dipole forces. There would be other intermolecular forces, whatever they are, in all directions. Above and below, left and right, side to side, top and bottom. So in the bulk liquid, the intermolecular forces are everywhere around the molecule. On the surface, those molecules have intermolecular forces to the left and the right and in front and in back and below, but not above because they're on the surface. And so if you added up the forces, the intermolecular forces on that molecule, it adds up to something with a downward component to it. So all the surface molecules have intermolecular forces pulling them down essentially. So you get kind of a skin on the surface. It's not literally a skin, it's not something you can peel off, but it behaves that way in certain ways if the forces are strong enough. Water has a high surface tension, and you can skip rocks on water. You can float leaves and paper clips and things like that carefully on water. Bugs can walk on water, but not on something like benzene or methylene chloride or something that's more nonpolar. Not much surface tension, because even though there are intermolecular forces, they're weaker. They're dispersion forces or something that are a little weaker than the hydrogen bonds for small molecules. And so you don't have much surface tension in a nonpolar substance like hexane or something. Not much surface tension. You could try to skip a rock across hexane, it's gonna fall in. Another interesting thing about water compared to many other substances is this phenomenon called capillarity, sometimes called capillary action. Capillarity gives you what is called the meniscus. If you've taken a chem lab, you know what they tell you about reading the volume of water in a piece of glassware, right? If it's a graduated cylinder, a burette, a pipette, whatever, read the bottom of the meniscus, they say, right? And the meniscus is that concave shape because the water molecules, they have hydrogen and oxygen, so they can do hydrogen bonding. The glass contains oxygen as well. All glasses, it's a silicate material based on silicon dioxide, is the empirical formula. It's actually usually bonded many, many times over many, many atoms, but the empirical formula to start with is SiO2, but in combination with other things. It's not just SiO2. If you buy lab glassware, Pyrex, Chymax, whatever brand is on sale, it's got boron oxides in it. There's sodium carbonate used in making such glasses. All those things have oxygen atoms in them. So the surface of the glass has oxygen atoms that can hydrogen bond with the hydrogens in the water. And so water forms good hydrogen bonds with the glass. And it can creep up the sides. Do you notice a meniscus in a very wide container? If you have a wide, shallow dish and you pour water in it, do you notice any concave meniscus? Not really, right? It does creep up the sides a little, but if it's too wide, you don't see it. The meniscus is very noticeable in narrower glassware. If you have very narrow glassware, the meniscus becomes very pronounced. It can creep up the sides quite a bit. And so very, very, very narrow glassware, you get a very, very, very pronounced effect where the water actually creeps up the glass a little more than you might expect before it can't support its own weight anymore and it forms the meniscus. So capillarity results in the shape of the meniscus, and sometimes for very narrow glassware or other fibrous things, it'll actually creep up. Mercury has the opposite shaped meniscus. This is less common to see. Used to be you could get a mercury thermometer in like CVS to see if you had a fever. And they don't sell them much of anywhere anymore. We used to have whole drawers full of mercury thermometers in the chemistry departments because that's what they'd, like in your drawer for Qual Lab would be like a mercury thermometer. And they'd break, it was a mess, it was dangerous, you got to get the mercury spill kit out and call health and safety and all this stuff, and never mind the broken glass, the mercury was dangerous. So we don't have the mercury thermometers or barometers or anything out that we used to. But mercury has metallic bonding within the substance. And the metallic bonding in mercury is so strong within the substance, it's much stronger than any forces that it might have with the glass. There's really nothing going on between mercury atoms and the glass than dispersion forces. So the mercury sticks to itself more, and it forms this convex shape, meniscus. So if you're reading something with mercury, not that you see this much anymore, the convention with mercury is actually you read the top of a mercury meniscus because it curves the other direction. And the amount of curvature depends on the width of your glassware. Once again, a wide dish of mercury, you don't notice the meniscus. It does actually creep up from the glass a little bit. A very thin tube, it would be a noticeable curvature. So that's another interesting thing about water, that capillarity actually does give it some properties. And this figure is it's a fanciful figure that is in one of the older editions of the textbook, with at the roots of the properties of water, the atomic properties, hydrogen and oxygen, just the numbers of protons, neutrons, and electrons, the sizes of the atoms, the electronegativities. Those properties give the molecular properties of water, like its shape. It's a bent molecule because of the number of electrons. It's a polar molecule. Being polar, it's a good solvent for ionic compounds. There's ionic compounds everywhere, right? In seawater, in natural fresh water, in bodily fluids. And it has, besides polarity, it has hydrogen bonding that makes it a good solvent for not only sugars and proteins, where there's lots of hydrogen bonding as well, but O2 and CO2. We mentioned them the other day. They are nonpolar, but having oxygen atoms, they can hydrogen bond, right? A molecule of CO2 can form a hydrogen bond with an H2O molecule in solution because the oxygen in CO2 has a lone pair. And that's what you really need, is the lone pairs on oxygen. So O2 and CO2 are water soluble, thank goodness, for aquatic life. The heat capacity of water, we've seen that last semester with Q equal MC delta T. We mentioned it again more recently. It takes a lot of energy to warm water up a little bit compared to other substances. If you put the same amount of energy into heating a sample of most metals, copper, lead, many other liquids, the temperature of those materials would change by a lot more than water does. And this helps keep narrow ranges of temperature. There's so much water on Earth that mediates the temperature on Earth. So much water in your body mediates your body temperature. A lot of heat changes your body temperature, but not as much as if our blood were using like carbon tetrachloride or something as the solvent. The heat capacity is less, and so the same amount of heat would heat up the carbon tetrachloride by a lot more, and we couldn't keep a narrow body temperature range. So that's a good thing about water. The open ice structure, remember the phase diagram? We mentioned that the slope of the solid liquid line indicates that it has a less dense solid than the liquid is. And this is good for aquatic life in winter, that a pond freezes from the top down, that the stuff underneath can stay in the liquid. The liquid is relatively high in density, and that actually it's interesting. Liquid water is densest at 4 degrees Celsius. So as water cools, it gets denser, and then as it continues to cool, it gets less dense. And so this results in turnover in bodies of water because of the density being a function of temperature. As the water cools, it rises and falls, or falls and rises, I guess I should say. And this helps in a lot of geologic processes as well as the nutrients in lakes. The heat of vaporization, what's at 44 kilojoules, is nice and high. For a molecule its size, it's really high. And this also is important in regulating body temperature. A lot of heat can go into evaporating a little bit of water instead of evaporating a lot. So that's a good thing. You don't get dehydrated as fast by evaporating. I mean, you could evaporate a lot more water if it was only a few kilojoules per mole. And that also goes into weather, right? There's phase changes in the weather between liquid and gaseous water. And surface tension and capillarity, we just mentioned. Capillarity actually finds its way into things like water going up a tree or a tall plant or something against gravity. Gravity's not that important for individual molecules. But when you start to think about a bulk quantity of water, how are you going to get water up to the top of a tall tree or something? Part of it is capillarity. Part of it is that capillary action that makes the water be able to creep up through small pores and things. So it's an important thing for all of our lives. So water's kind of neat. For the size molecule it has a lot of behaviors that larger molecules should have. Large heat capacities and large heats of vaporization and things like that. But if it were that large a molecule, it wouldn't be practical for other things. So it's a kind of neat molecule. That said, it's a important aspect of the next thing we're going to do. We're going to do one more thing with solutions. It's a little more quantitative enough, but it's not terrible. So it's a cute figure, though. The first author of the textbook, Martin Silberberg, is a chemist and an artist, both by profession. So he did a lot of the artwork in the original versions of the textbook. And kind of some neat art, like the art. So, last thing on solutions is a topic called colligative properties. And colligative properties are they're both a concept and a quantitative thing. That is to say, they have numbers involved. Colligative properties, by definition, are physical properties of a solution that depend on the concentration of the solute, but not the identity of the solute. That is to say, if I have the same number of solute particles in a certain amount of solution, it doesn't matter what those particles are. The colligative properties would be the same for those two solutions. To do this kind of thing, we're going to make a couple of assumptions that simplify life. you could get away without making all these assumptions, but it makes things more complex. One simplifying assumption is we're going to assume that the solute particles are non-volatile, or volatile, if you like, whichever way you like your vowels. Volatile refers to something that has a vapor pressure. If something is volatile or volatile, it has a vapor pressure that's not zero. Non-volatile means no vapor pressure. Okay, so it's a different use of the word than everyday usage. It's like spontaneous. In everyday usage, it kind of means a different thing. If there's a volatile situation, it might turn into a crazy fight or disaster or something. That's a different sense of the word. You can do this with a volatile solute. It's not that hard. It just adds to it in a way that we don't need to worry about at this time. I'll point out when we're looking at this where the volatile solute change would be made. It just adds another step to it. It's not it's not that you can't do it. If we wanted to do it, I'm confident you could handle it. It's just not something we got to worry about. So we'll skip volatile solutes for the time being. Also, we're going to assume ideal behavior, that is to say dilute solutions, similar sized particles for the solute and solvent, no huge macromolecule proteins or something necessarily. Similar intermolecular forces. The further from ideal you get, the more tweaking you have to do to the numerical results. The concept is the same. The numerical answers are thrown off by non-ideal aspects. So we'll mainly focus on the ideal case, kind of like using PV equals nRT for everything, knowing that sometimes that doesn't give you perfect answers, but most of the time it does. Same idea here. There might be things where it doesn't work perfectly. Now, experimentally, this is what's observed when you have a solution compared to pure solvent. Panel A of the cartoon figure 13.23 shows at equilibrium, pure solvent with vapor above it. So we have at a certain temperature, let's say it's water. I don't know, whatever. It doesn't matter what the solvent is. Okay, we got solvent, and it's in a closed system, and it has a vapor pressure that we can measure, so many torr, whatever it is. Now we make a solution of it. The dark circles here are solute particles, and we know they're non-volatile because there are no dark circles in the gas phase. Right? If it were a volatile solute that had a vapor pressure, there would be dark circles up here, right? But there aren't any. So that's non-volatile. It's easier that way. Okay. So the solute is non-volatile. Notice that it looks like there's less vapor above the solution than there is above the pure solvent. You see that it looks like there's less vapor, fewer gas molecules? And that's not a mistake. It's not a typo. Experimentally, that's what's observed. The vapor pressure above a solution is lower than the vapor pressure above pure solvent at the same temperature. Now, why does this occur? There are still some sources out there that say this horrible explanation, and hopefully you've never heard it before. But there are still folks that will say, oh, the solute molecules block some sites at the surface that the solvent would evaporate from. They can't get to the surface to evaporate, so the vapor pressure is lower. Okay, that is fake chemistry news. Okay, that's really, really bad as an explanation. Even a dilute solution exhibits this. In a dilute solution, not enough sites will be blocked at the surface to make a difference. It has nothing to do with blocking surface sites. If you have a system with nothing on the surface and you measure the vapor pressure, let's say water, and you have it in a closed system, they've verified this. Have a tank of water and a very large closed thing, measure the vapor pressure at equilibrium, then have the same container of water and put things on the surface floating and measure the vapor pressure. It's the same vapor pressure. It doesn't matter if you block some sites on the surface. The vapor pressure is a function of one thing, the temperature, not of how much surface area there is. Okay, so that's not the explanation. The explanation for this phenomenon revolves primarily around entropy. The entropy of the first system there is a certain amount, and the second system, the solution, can achieve the same total entropy with less gas because the solution has a higher entropy itself. The solution is higher in entropy, so to reach the same overall entropy, you don't have to have as much gas. So it revolves primarily around entropy. It's nothing to do with sites on the surface where things can evaporate from. If you've ever heard that before, that's seriously something that you want to get rid of as an idea, because it's bad. Okay, and there's still things out there that say our textbook has been pretty good all along about that, but there's certain textbooks that, it's one of those things that it's better to say nothing about and just say this is what happens, period, full stop, and then to explain it wrong. So if you've ever heard that explanation, get it out of there. So vapor pressure is lower for a solution versus a pure solvent, for the solvent. And that's where it gets tricky. Let's say that the solute were also volatile. It would have a vapor pressure as well, and then we would have to have two vapor pressures and add them up with Dalton's law of partial pressures to get a total pressure. It's not undoable. It's all stuff you've heard of before. It's just it's confounding to what we're doing at the moment. All right. Quantitatively, the vapor pressure of the solvent above a solution equals the mole fraction. That X there is the mole fraction. It is actually technically typeset as a capital Chi, but most fonts, it's imperceptible, the difference, and so they usually just end up using an X, often an italicized X, but italics don't always seem to want to stay put. So X is often used in place of a Chi because they look like each other. I know they're not really the same thing, but that's all right. My friends in Sigma Chi would have made a stink, but that's all right. So X is the mole fraction of the solvent times the vapor pressure of the solvent as a pure substance. The circle there is for pure. Okay. So for example, pure water, 20 degrees Celsius, the vapor pressure is about 20 torr. And let's say we had a solution that was 4 moles of water and 1 mole of something else soluble in water that is non-volatile. I don't know. I'm trying to think. I don't know if a whole mole of glucose will dissolve in 5 moles of water. That's kind of iffy. But let's say that was a solution that existed. Okay. The mole fraction of water there would be 4/5, right? There's 4 moles of water, 5 moles total. 4 moles of water and 1 mole of solute. And so 4/5 times 20 would be 16 torr. So the vapor pressure above that solution would be 16 torr. 4/5 of 20 torr, the pure vapor pressure of water. So we see that if it's pure solvent, the mole fraction's 1. It's the pure vapor pressure. And so the more concentrated the solution is, the lower the vapor pressure would be. Goes as the mole fraction. And they use sometimes just letter A. And then if you have multiple components, you could have A, B, C. You could do this over a series of components in the same solution. That's where volatile solutes could come in. Let's say that we had a volatile solute as well. It would also follow this thing called Raoult's law. So for the solvent, you'd have a Raoult's law equation. For the solute, you would as well. So, the other component, let's say that 4 moles of water and 1 mole of solute, whatever it is, the mole fraction of solute would be 1/5. 1 mole of solute over 5 moles of everybody. And if the solute had a vapor pressure in that solution, its vapor pressure above the solution would be 1/5 of what it would be pure. So you can do it for a mixture with a volatile solute. It just adds other numbers. It's not a big deal. But we're not going to worry about the solute. We're focusing on the solvent here. So Raoult's law applies to each component of the mixture. And once you got those partial pressures, if you had PA, PB, PC, etc., you can add them up using Dalton's law. So this is just total name dropping at this point with Raoult and Dalton and everybody else. So ideal solutions follow Raoult's law perfectly. Real solutions follow it when it's dilute. If it's more concentrated, there are fudge factors you have to apply. Kind of like when we mentioned about using molarity instead of activity in equilibrium constants and stuff. There's a coefficient that can be applied for correction, but we'd rather not if we don't have to. Now, I used to have a derivation of the next boxed thing here in the notes, and nobody cared, not even me. So we got rid of it. That the change in the vapor pressure, it turns out, you can derive this, it's in the textbook, is equal to the mole fraction of solute times the pure vapor pressure of the solvent. So this is vapor pressure of the solvent here. Because the mole fraction, if it's a 2-component mixture, you could start out, this is where it kills you, is if it's 2 components, it's easy to derive. Because the mole fraction of solvent would be 1 minus that of the solute, and then you start multiplying and substituting. You get to this, it's fine. So we see that the vapor pressure is lowered more the more concentrated the solution is, right? The more solute there is in terms of mole fraction, the greater the lowering of the vapor pressure is going to be. It makes sense, right? There'll be less solvent, so its vapor pressure will be lowered. And this is, mathematically, you might not buy that equation totally, but you can derive it. It's just, I had it in the notes, and it took up 4 or 5 lines, and literally, no, it was one of those literallys. It's not one of these literallys that doesn't mean literally. This was seriously, no one cared about the derivation, including myself, so we got rid of it. But you can get that. So the vapor pressure is lowered, is the upshot. When you make a solution, the vapor pressure is lowered. So go to the phase diagram. Here's the phase diagram for water, but it would be actually correct for any phase diagram for any solvent. So this is figure 1324. The solid lines are for pure solvent. And we know this must be water because that solid liquid line has a negative slope, right? Most solid liquid lines would have a positive slope. This one is negative, so it must be water, or maybe bismuth, but probably not. So, all right, the solid lines are pure water. The vapor pressure is lowered. So here's the vapor pressure of liquid water, and we're going to go lower at the same temperature. Same thing over here. We're going to go lower at the certain temperature on that liquid solid line. Okay, so we have to drop down. So the dashed line is for a solution. Now what this means is for our lives, what we're going to observe is that this water, in this case it's water, but it would be true for any solvent, it's going to freeze colder and boil hotter than if it were pure, right? The freezing point and boiling point are where the 1 atmosphere value crosses those lines. And so those 2 points, the circled asterisks there, are the freezing point and boiling point of the solution. So it's going to freeze colder and boil hotter than pure water because the vapor pressure is lowered for your solution. We widen the liquid range a little bit. Turns out it's not by a lot necessarily. So the vapor pressure is lowered. The freezing point is depressed, and the boiling point is elevated. I don't know why they choose the words they do. They say vapor pressure is lowered, but freezing point is depressed instead of lowered. They could have said raised and lowered for boiling point and freezing point. They chose elevated and depressed just to have different words. Depressed sounds so clinical or something, but that's what it is. Now, a delta T, they want to know quantitatively by how much is the boiling point elevated? By how many degrees Celsius is the freezing point depressed or the boiling point elevated? Delta is always final minus initial, right? This is a killer in this chapter. I don't know why they do it in just this one place. Delta is always final minus initial, right? If you're doing Q equals MC delta T, it's final temperature minus initial temperature, and if you have it backwards, you get a wrong answer, right? You would have the wrong answer for Q, right? But in chapter 13, when they're doing freezing point depression, for some insane reason, they say, we're going to have all our deltas be positive. Direction be darned, right? So they do that. It's not the original way they did it, but it's getting more common in books because apparently they just, they don't like deltas being negative numbers for some, which makes no sense. Everywhere else in the textbook, a delta can be positive or negative because it's final minus initial, right? But not in this one place. So if you're reading that, they don't do it that way in the textbook. I'm trying to help you out here, especially on the equation page. So I've got a minus sign where the textbook might not have it, but it's there to help you, okay? The change in boiling point would be the boiling point of the solution minus that of the pure substance. Same for freezing. Solution minus pure. And so if you solve that for the temperature itself, that's, original, pure, plus delta. That's how it should be. Where freezing point, the delta would be a negative number, right? If the freezing point is depressed, it means it goes down. So the solution would be less than 0. So these are the equations that show up on the equation page. Actually, they're not quite. They're close. We'll show you what's on the equation page. The equation page version is slightly tweaked. Delta T, boiling point change, is Kb, that's a constant, times m for molality. And we'll get back to molality. That's the concentration. For these, we use molality, and we'll return to that in a second. Freezing point depression is minus Kf times m. I like to put the equation with a minus when I provide it because it's a Q to U. The freezing point goes down. Okay? If it just says delta TF equals Kf times m, then it is up to you to remember which one goes up and which one goes down. And I'm trying to help you out, okay? So I know the minus sign is not in the book, but do you understand my reasoning for putting it there? I'm trying to help you out because the way they do it in the book is silly. Delta in any other section of the book would be final minus initial, and this delta is somehow not that way because they think it's easier. I don't like it. But that's why the minus sign, okay? So it's always final minus initial, solution minus pure solvent, and the minus sign is there to help you remember that when you have a solution, the boiling point goes up and the freezing point goes down compared to pure solvent. And that's why the minus sign, okay? So it's not, I'm not being ornery or an old fart about this. I'm trying to help you out, okay? Now, we use molality. That L capital in the middle of a word is not a typo. It's there to get your attention. If you were reading that real fast, you might read it as molarity and not notice it's molality. Molarity is not good if you're changing temperature. If you want to keep a lot of sig figs on your concentrations, molarity is moles per liter, right? It's moles of solute per liter of solution. And density of substances is a function of temperature. If you're changing the temperature, the molarity is going to technically change because the density of your solution is going to change. Is it a huge effect? Not over a small temperature change. But if the temperature changed by enough, it's going to change your molarity in, say, the third or fourth sig fig. And if you're doing very sensitive work, then you'd like to keep those sig figs. So molarity is not the unit of choice. Molality is for this, because molality, as you recall, is moles of solute per kilogram of solvent. And those are unchanging with temperature. That's why we use molality. Okay, it's temperature independent. So we use molality, little m. The symbol for molality is a lowercase m italicized. That's the technical symbol for it. And that's the unit symbol after a number. Lowercase m not italic is meter. Lowercase m italic is molality. It seems nitpicky. Oh my God, you mean italic makes a difference? Yes, it actually makes a difference. If you're writing a senior thesis and Dr. Tessier's checking it out or something, they check for format, things like that. So it's got to be technically done right. So the m is italicized for molality. Kf and Kb are constants for a particular solvent. So, for example, there are values of Kf and Kb. Those are the constants for freezing point depression and boiling point elevation. They're a particular value each for water. And it doesn't matter what the solute is, right? Because these are colligative properties. They don't depend on the identity of the solute, only on the concentration. So it doesn't matter if it's a 0.1 molal solution of glucose or sucrose. They're both 0.1 molal solutions. The colligative properties will be the same. So you just look up the Kf or Kb values for water if it's an aqueous solution. What if it's not aqueous? What if it's in hexane? Well, there's Kf and Kb values for hexane and benzene and everything else. So those are data values, unless I suppose there was some question about actually calculating Kf from the other information. But Kf and Kb, it wouldn't be a good question on a test to ask use this information to get the value of Kf for water, because it's already on the equation page by the waving hand here. So those are the values over on the left-hand side. Kf for water and Kb for water. Those are the values in degrees Celsius per molal unit. Or Kelvin per molal if you like, right? It's a temperature change. These go into an equation that's with delta T. So they could be Kelvin per molal if you really wanted them to be, because your temperatures would be in Kelvin. So, all right, we use molality. Kf and Kb don't depend on the solute, only on the solvent in use. And we're going to raise the boiling point, lower the freezing point. Shall we try a calculation, see what kind of effect these have? Well, let's try one. We got the space here, left wide open space to do it. If I can get it to work, there we go. Okay. All right. So let's say I'll write it as a nice imperative sentence. Calculate. Hey, you calculate the boiling point. Let's say at 1 atmosphere, just to make everything completely unambiguous. That's, on the cover of the exams, I always have, unless otherwise stated, it's 1 atmosphere, 25 degrees, blah, blah, blah. That's to cover myself if I forgot the parenthetical. So otherwise people could say, I can't do that because you didn't say what the pressure was. So this gets me out of it. So calculate the boiling point at 1 atmosphere of a solution. Whoa. I just tried to dot that I. Prepared. Think the word prepared will fit? Wow, just made it. Okay, by dissolving, let's say, I don't know, 85, I don't know why I need a decimal point there. I'm not making another number. 85 grams of C6H12O6 in, I don't know, why not 2.1, well, why don't I write it this way? Why not 2,100 grams, sure, of water. Okay, so the C6H12O6 is glucose. Actually, there's more than one C6H12O6. I'm going to say it's glucose. It could be, there's another O that it could be as well. If this were on the exam, there'd be a box with the molar mass because you need it. So since we need it, I'll write it down. (180.16 grams per mole). So, you know, in the usual style of the final exams and the exams I write, because I like to make them look like that, there'd be a molar mass in a box. And then on the data page, on the equation page, is another piece of information, right? This is a boiling point elevation question. It's a solution. They want the boiling point. It's not pure water. So we need Kb, right? You're going to look at the equation page. Kb for water, as it says on there, is, was it 0.512 degrees Celsius per molal unit. Okay. So that's all the information we need. Now we just got to figure out how to solve the problem. Okay, so calculate the boiling point of that solution. So first we got to, I guess, figure out the molality. And then calculate the the boiling point elevation using the molality. And then we'll add the freezing, why I keep wanting to say freezing, I guess because it's so cold out. Then we'll add the boiling point elevation to the original boiling point, which is 100, right? The pure water would be 100 degrees Celsius. So this is going to boil at higher than 100 degrees Celsius. That much we know. How much higher? That we have to calculate. So, all right. The first step would be to get the molality itself, right? So it's going to be the moles of glucose. That's the C6H12O6. Moles is going to be, let's see, I got 85 grams of it. I got to do grams to moles on that, right? I got to convert the 180.16 grams to moles. And then once I've got those moles, I can divide by the kilograms of water. That's the solvent. This is molality, right? So I want moles of solute divided by kilograms of solvent. That's my molality. So 2,100 grams, I've got to convert that to kilograms. So it might seem OCD to write grams of C6H12O6 and grams of water and stuff, but you might recall if you were doing grams to moles to grams and stuff, that if you have grams of more than one thing in a problem, it's good to mark which thing. Because you could easily accidentally have the wrong grams on top or start canceling the wrong grams and you get a totally wrong answer, right? So it might seem a little OCD to write H2O and C6H12O6 and all this in here, but it really isn't if you're worried about getting the units right. So the grams cancel on both of those. So now I got moles of glucose divided by kilograms of water, and we'll try calculating this and seeing what, if someone else does it too, then I will trust their answer more than my own. 0.4718 moles divided by, that's 2.1, right? 2,100 by 1,000. That'll save a little bit. 2.1. Okay, so I got 0.225. Yeah. Anyone else got the same answer? Yeah. I trust you guys. Okay. So I'm going to write down extra. At the end, we'll have to round to 2 sig figs on something, but for the moment, in case this calculator gets totally screwed up, I'll write down 0.225 anyway. Okay, so that's the molality of the solution. That's not the final answer, right? That's just the first step. 0.225 molal. And then the boiling point elevation is Kb times the molality. So it'll be 0.512 degrees per molal unit times my 0.225 molal. That cancels the molals. And this is not looking good for it being a lot of temperature change, right? I haven't calculated the number yet, but this is like a little less than a quarter times a half a degree. This is not looking good for a huge amount of temperature change. This times 0.512. Ouch, 0.115 something something. Okay, so that is not a huge temperature change. 0.115 degrees Celsius. So the boiling point would be the 100 degrees, which we can put a couple decimal places on that, because that was the definition of 100 degrees Celsius. That was, water. The normal boiling point of water was calibrated to be 100 degrees Celsius. So we can get away with a couple decimal places, thank goodness, right? Otherwise, if we had to round it to the nearest degree, it would round back down to 100. You wouldn't be able to tell a difference. So we can put 100.00, that's fine, plus the 0.115. I'm going to have to round that off. It's going to be 100.12 degrees Celsius for my final answer, rounded, because that should be rounded to the hundredths place, right? The delta T should be 2 sig figs, based on the data that I had. So properly rounded to 2 sig figs, it would be 0.12, and then I'll get this dangling end of a quadrilateral here. It just is ugly. Yeah, there we go. I don't know what that is. It's just a quadrilateral, I guess. It's not a trapezoid or something. I don't know what it is, but whatever. 100.12. That's hardly even possible to measure, right? If you're taking Qual Lab and you did that physical properties of water with the, freezing the water and getting the cooling curve and all this and everything, 0.12 degrees is probably well within the error of your measurements, right? This is very tough to measure. You'd probably have to do it with very sensitive equipment and be very careful. Or probably, if you needed to do something like this, maybe have a more concentrated solution. I mean, this low molality is not helping. But then again, if it's too concentrated, it's not going to be an ideal solution. It's going to start straying from this equation anyway. So the boiling point is elevated, but in the case of water, not by much. It depends on the value of Kb, right? If Kb were larger, if Kb instead of 0.512 were 5.12, then we'd get 10 times the elevation. Wow, it would go up a whole degree plus 0.2. Wow. Ooh, it still wouldn't be that much, right? Even with a 10 times larger value. So it doesn't go up by a lot for water. Looking at the data over here on the side, we see, looking at those values, there are the values. Kf for water is closer to 2 degrees. It's still not a huge number, but at least it's larger than the boiling point change is. So, yeah, you get changes in the boiling point and freezing point, but not by a ton for water. There are other solvents with larger values. There are certain organic solvents that have a Kf that's 6 or 7 degrees per molal unit. And so you can get a big bang for your buck. But water is not changing that much. So, don't expect the solution to boil a lot measurably higher based on a pretty dilute solution. It's going to be tough to even measure that, especially if you're boiling. If you're boiling in an open beaker, it's not even reaching equilibrium, and so it's going to be tough to measure. But it's a good thing to be aware of. So we could also calculate the freezing point of that solution, right? It would just be a different value here. Instead of Kb, it would be Kf. So we'd have 1.8. Oh, great! It's erasing everything. That's good. I'm going to stand there. This will be like the person who writes with one hand and erases with the other at the chalkboard. I can just erase what I just wrote. Instead of K, hello! People who are listening to this recording are going to love it. They have no idea what's going on. If they could just see I need a technical difficulties slide to put up, like at a TV station. They put the thing up and, there's like the dog with the power cord pulled out and everything. Plug that back in. So instead of Kb, we put in Kf, different number. We'd get a delta T freezing. It would be a negative number, right? That's why I like the equation with the negative sign. So as a reminder that when it's a freezing point thing, it's going down. That's why I like the version with the negative sign. It's not that way in the book, but I'm trying to help you out. And so it would be minus some number of degrees, and then we'd add that to 0. And it would be below 0. So that's fine. We could do that too. It would just be a different number. We could do it. but there's bigger fish to fry. By the way, if you gave up doing chemistry homework for Lent, that's over. You can return to doing chemistry homework. Speaking of fish to fry. All right. So anyway, that's numerically the freezing point depression and boiling point elevation. But there's a twist. You knew there'd be a twist, right? Can never leave well enough alone. I used glucose in that problem for a reason. The glucose is a non-electrolyte. And that's intentional to start with a non-electrolyte. What if you have an electrolyte as a solute? Remember the term electrolyte? It's back in chapter 4, the very first time we see it. If a solute is an electrolyte, what does it do when it dissolves? It ionizes, right? If it's a strong electrolyte, it ionizes completely. If it's a weak electrolyte, it ionizes to some smaller extent. Weak acids, weak bases. We love weak acids and bases, right? We can calculate so many things with pH and stuff with them, right? They're great. Percent dissociation. What's the percent dissociation of a weak electrolyte? Less than 100, right? And usually it's way less than 100, 5% or less. So an electrolyte ionizes, which means it gives you more particles than you started with. So we have to introduce a fudge factor. Fudge. The Van 't Hoff factor is the fudge factor that is inserted into the colligative property equations. The symbol is I. It's not the square root of -1 for electrolyte solutions. It's the ratio of the measured colligative property for an electrolyte solution to what the colligative property would be for a non-electrolyte solution of the same concentration. That is to say, as a concrete example, let's say I had a 0.1 molal solution of glucose versus a 0.1 molal solution of NaCl. So the recipe is basically the same for both, right? Going to take 1/10 of a mole of solute, and we're going to know how much that is by getting the molar mass from the bottle or something, and then taking 1/10 of that many grams, and we're going to dissolve it in a kilogram of water. Stir it up. They'll both dissolve. So I get a molal solution of sugar and a molal solution of salt. Glucose is a sugar. NaCl is the salt known as salt. And it turns out they have different boiling points, different freezing points, and different vapor pressures, even though they're both 0.1 molal, because in NaCl, a reaction occurs, right? Maybe you can fight over whether this is a reaction or not. Maybe the neutral word to use to not offend anybody's sensibilities about that is this process occurs. The NaCl, when it dissolves, forms a pair of ions. So, if I got 1/10 of a mole of sodium chloride and I dissolve it in my kilogram of water, how many moles of particles are there dissolved? 2/10 of a mole, all right? I get 1/10 of a mole of sodium ion and 1/10 of a mole of chloride ion. Oh, I got so close to making it. I could have scrolled over more, but then I'd fall off on the other side. I'll fix that later. There's margin I could have written in, but then I'd cut off on the left-hand side. So we'll fix that later. No, I won't. It'll be like that when I print it. So there's actually twice as many solute particles there as the concentration on the label indicates, right? Because it's an electrolyte. And so the fudge factor here for sodium chloride would be 2. Because you get twice the solute particles, so you get twice the boiling point elevation, twice the vapor pressure lowering, twice the freezing point depression, because colligative properties don't care what those particles are in the salt solution. It doesn't care that half of them are sodium ions and half of them are chloride ions. All it cares about is the fact that there's 2/10 of a mole of particles dissolved in the kilogram of solvent for a total molality of 0.2, not the 0.1 in the bottle, because it's an electrolyte. So if you have an electrolyte, then you have to use the Van 't Hoff factor. The equations on the equation page are already fudged for the Van 't Hoff factor. So there's the freezing point and boiling point change equations there. Note, you see the boiling point one has the negative sign. Again, trying to help you out, trying to make sure you remember which one goes up and which one goes down. It was easier when it was done the right way. Back in the day, uphill both ways through the snow, things had negative signs. So I is the Van Hoff factor. Now, that's the ratio that's measured. This is the thing. The theoretical Van Hoff factor is 2 for NaCl. And so you'd put 2 into all those equations. You have twice the vapor pressure lowering, twice the freezing point depression. However, in a real solution of NaCl, you don't actually get that. It mentions here, ideally for NaCl is 2, but let's say you had a 0.05 molal solution of NaCl. That's not that concentrated, right? We're talking about 1/20th of a mole of NaCl in a whole kilogram of water. So let's see, NaCl is like 58 grams per mole, 58.5 grams per mole. So 1/20th of that is not very much, right? It's going to be 0.05 times the, oh boy. So it's not very, a tenth of a mole would be 5.5 grams. It's going to be half of that's going to be 2.5 grams-ish. A couple grams of NaCl in a whole liter of water. A liter of water weighs a kilogram, right? Mix it up close enough to a kilogram, and you get 1.9 times the freezing point depression, not twice, only 1.9 times. And that's a fairly dilute solution. Why only 1.9? These ions pair with each other. In solution, if an Na plus and a Cl minus bump into each other, they kind of attract each other. They might kind of stick to each other for a moment. And this happens throughout the solution from time to time. As some of them separate, others might come together. That's decreasing your head count, right? An associated pair of ions counts as one particle, not 2. And so it's going to decrease your head count of ions. It's going to effectively decrease the concentration from 0.05 a little bit of dissolved particles. It's still 0.05 moles of salt per kilogram of water, but in dissolved particle terms, it's not twice 0.05 moles. It's a little less than that, as measured by experiment. So you get 1.9 times the freezing point depression and stuff, not twice. That's all right. That's fairly dilute, and it's still not behaving perfectly. What if it were 1 molal? 20 times the concentration. It would be even worse. It would be down from 1.9. So it doesn't give you perfect answers for electrolytes. That's why, if you wonder on colligative property questions, why are there so many questions with weird sugars and things as solutes? Why don't they just use like NaCl or something? Electrolytes don't behave very well. They give you these ion pairs that decrease the colligative properties. So you end up using every glucose, sucrose, fructose, galactose, every ose there is or something as a solute to avoid, to have something that's a non-electrolyte. You can't even use something like ammonia, right? Ammonia would be even worse. Ammonia is a weak electrolyte. How many ions does it form? Oh my God, I have to do an ice table problem to figure that out, right? I have to calculate what X is in a quadratic or hopefully simplify it. It's not the label concentration, and it's not twice that either. It's something in between. So we avoid weak electrolytes because they're a little messy. So let's say we had, just for one more comparison to make, let's say I had solutions of these things. Let's say I got the glucose and NaCl, and why not, I don't know, a sodium sulfate and an aluminum chloride. They don't all have to be sodium. I could have used a sodium phosphate. It would have been the same difference. Which of those 4 solutions would have let's say, the highest boiling point? Could ask about something else. Highest boiling point, why not? Comparing those 4, which of the 4 would have the highest boiling point? Or are they all the same? If this were on the exam, this would be like A, B, C, D, and then E would be, they all the same. Aluminum chloride, okay, why? More ions, yeah, so it dissociates into more. I would be 4 ideally. Consider what these form when they dissociate. First one's a non-electrolyte. The second one we saw is Na plus and Cl minus. The third one is 2 sodium ions and a sulfate ion. We'll neglect the fact that the sulfate ion is a weak base and it would hydrolyze and give ions as well. We're not worried about that. The chloride ion is a nice, very, very weak base that we don't have to bother with. And the aluminum chloride gives you an aluminum ion and 3 chloride ions. So going down this, we get 1, 2, 3, and 4 particles, respectively. So I would be ideally equal to 1, 2, 3, and 4 going down there. Usually we wouldn't even talk about I equals 1, right? I mean, I is for an electrolyte, but for a non-electrolyte, you can treat I as being equal to 1, right? You can get into philosophical arguments about whether there is a Van 't Hoff factor at all for a non-electrolyte. But mathematically, to use one equation, we'll just say there is and call it 1. So the fourth one, the aluminum chloride, gives you the most particles for every dissolved mole. That would give you the biggest colligative properties, right? It would have the biggest lower vapor pressure lowering. So it would have the lowest vapor pressure. It would have the highest boiling point. The T in highest became capitalized. That's pretty good. And the lowest freezing point. The aluminum chloride. It would have the lowest freezing point because pure water starts at 0 and all the solutions would be less. And the aluminum chloride would be the less by the largest amount. So it would be the furthest below 0. When you're talking negatives, it gets confusing sometimes. Is that clear why it's the lowest freezing point? It has the most freezing point depression, but you're going negative. So you're getting further from 0 on the negative side. So it would be the lowest freezing point. It has the most freezing point depression, or that's a negative quantity. I like the equation with a negative sign in it. It just seems to clean things up a lot. So it's a bigger negative change. So more concentrated, it would also change. But is it going to be actually 4 times the freezing point depression and boiling point elevation compared to glucose? No, of course not. It's going to be, I could have used sodium phosphate, but I chose not to. I could have used Na3PO4. That would have also been 3 sodiums, 1 phosphate, also a total of 4. But it's good to spice it up a little bit. But for sodium phosphate, for a 10th molal solution, the measured Van 't Hoff factor is about 3.4 instead of 4. It's quite a bit lower. For aluminum chloride, I'd have to look it up, but it's probably about the same. Because it's a +3, -1. Sodium phosphate's a +1, -3. Probably about the same. So, they rank correctly, though. Okay, it's going to deviate from the ideal, but it's never going to go out of order. It's not going to be like somehow sodium sulfate's the right answer. It's never going to be that out of whack. Okay. So that's another, Ellen's 12 days of exam question giveaways thing. There's always a question like that. It's easy to ask, right? Oh, God, if he's talking about Ellen, is he going to dance? No, I'm not going to dance. Don't worry. You don't want to see me dance. Did I tell you about the incident at a wedding reception one time? No. It's very simple. I was an usher at a friend's wedding, and we were doing the electric slide at the reception, and I knocked over a bridesmaid. It was terrible. I slid the wrong way. And then I had to lead the Macarena to make up for it. So that dates the story, actually, to about 97, I think it was. I think it was about 20 years ago. So, yeah. I can still do the Macarena. I'm very good at the Macarena. All right. So, anyway, that's the solutions. Here's going to whet your appetite for the next big item up for bids. We're going to get to it. We're going to finish it next week, but I can't tell if it's probably Tuesday, if not Thursday. We're going to get the model sets out. It's going to be very exciting. We'll have the model sets out, and people can work on building a couple of things I ask people to build, and usually it turns into a free-for-all of people trying to use all the atoms and bonds in the box in one large molecule. So if you do that, you'll have to take it apart afterwards when we do it next week. But a couple of things that really is easiest to build a model that you can see. And so there aren't enough model sets for one per person, but we'll have people work with a couple of neighbors on it. But we're going to look at transition metals next. And just whet your appetite a little bit on the transition metals. Transition metals are where you're filling the D subshells. This is in chapter 23, by the way. It's we're getting close to the end. It's not the whole chapter. There are a couple of sections of stuff that's a little more tedious than anything that we're going to not worry about. It's groups 3B all the way over to 8B, and then 1B and 2B if you number the periodic table the right way. If you insist on these numbers, it's 3 to 12. So it's the middle of the periodic table. You fill in D subshells. You've filled the 4S, 5S, or 6S first, and then you're filling the D that's one number down. But when you form a cation, you lose the S electrons first. So like iron is 4s2, 3d6, right? A ferrous ion, you lose 2 electrons, and you lose the 4s2 first. So you get 3d6 left behind. So most transition metal ions have partially filled d subshells, which results in some properties that are interesting. There's often more than one stable oxidation state. They often lose the S's, but sometimes they can lose one or two of the D's. So like you get iron that's +1 or +2. Iron can be +2 or +3. Copper can be +1 or +2. Some of them are +2 or 4 or 1 and 3 or things like that. Many of the compounds are colored. If you're taking the qual lab, you may recall, the iron compounds in solution are sort of orangey. The nickels are green. The cobalts can be a reddish color or so forth, so on. Whereas solutions of sodium salts, potassium salts, calcium and barium salts, aluminum salts are colorless. The compounds are white and crystalline. The compounds in solution are colorless. So transition metal compounds are often colored because the d orbital energies are such that they interact with visible light in a certain way where they absorb the right wavelengths of light that are visible. Also, magnetic properties are interesting. Interesting to whom? Well, maybe not you, but to somebody they're interesting. Magnetic properties arise from the electron configuration, and it is something that we've seen before. That, consider a carbon atom. It's 1s2, 2s2, 2p2, right? A bonded carbon atom doesn't have the same types of orbitals involved, right? A bonded carbon atom, you use sp, sp2, or sp3 hybridization usually. You don't use the atomic s and p orbitals because they don't give you the angles you need. They don't give you the results that are calculated or observed. Same thing with transition metals. An iron 2 ion is argon 3d6. But a bonded iron 2 ion in these compounds I'm going to look at in chapter 23 doesn't have 5 degenerate d orbitals. It may have orbitals that are split. A pair of orbitals here and 3 orbitals of a different energy. And how do the 6 electrons go? Do all 6 go in the set of 3 as 3 pairs? Or do they go 1, 2, 3, 4, 5, and then the 6th one again, and we end up with 4 unpaired? Depends on how far apart those orbitals are. That's part of the chapter we're not going to do extensively, but it's worth noting that it's the same kind of principle. If you consider atomic orbitals versus sp, sp2, sp3, the same kind of thing happens for transition metals. It's not hybrids like sp3. It's a different model of bonding because it's needed to understand it. But it's similar in concept to that bonded atoms often use different orbitals than isolated atoms do. And it results in interesting magnetic properties, that things are paramagnetic or diamagnetic that you might not expect. You might say, gee, an iron 2 ion is 3d6, it should be paramagnetic because there's 5 orbitals and 6 electrons, and you're going to get a pair and 4 singles. And it's diamagnetic. How can that be? Well, because there's 3 pairs. There's 3 pairs because they're all going into this group of 3 orbitals. The other 2 orbitals are separate. So it's interesting. We're not going to deal with it a lot, but it is of interest that it does occur. Now, the compounds we're going to talk about, just so you've heard this term, so it'll bounce around for a couple of days, are called coordination compounds. And the coordination compounds involve bonding between a transition metal and a thing called a ligand. And so I want to look mainly, look at these bullets down here at the moment, because we can get back to the set of 3 compounds next Tuesday. The transition metal in a coordination compound acts as a Lewis acid. And these things called ligands act as Lewis bases. There's the word ligand, if you're looking for it, L-I-G-A-N-D. It's there by the bullet. Ligands are Lewis bases. So in that first formula by E.G., everything inside the bracket is one particle with bonding, covalent bonds. So the cobalt is covalently bonded to the nitrogens there. The cobalt 3 ion is the Lewis acid. The ammonia molecule has a lone pair, right? If you draw the full Lewis structure with the sticks, the lone pair is still there. So the lone pair is donated to form a covalent bond to the cobalt, and you do the same thing 5 more times to make the 6 bonds. And so that is what the coordination word means. In coordination compound, you might recall when we talked about Lewis acid base, that covalent bond that's formed, but when the Lewis base donates to the Lewis acid, is called a coordinate covalent bond. And that's why these are called coordination compounds, because they have these coordinate bonds between the metals and these things called ligands. They're the Lewis bases. And so we got a couple different examples there. We'll look at them more on Tuesday. But everything inside the square brackets is a single covalently bonded particle. It's interesting. It looks like we got metals and nonmetals bonded to each other. That's fine. What about the things outside the brackets? What's going on with that? All your questions will be answered in our next episode. I feel like Rod Roddy at the end of an episode of Soap. Don't know what that is? Look on YouTube. All right, so that's all. Sorry, we'll do better the next time. No Tates, no Campbells, just coordination.